much. Okay. So sine and cosine functions model waves in real life. So whether it's a wave in an ocean, or it's an electromagnetic wave like a radio wave, a light ray wave, right? They all follow the same pattern, wave-like pattern. They're waves, and they're modeled by sine and cosine functions. Okay. The most important thing about sine and cosine functions is you can see an example down here, and basically as the x-axis extends to negative infinity and positive infinity, these waves continue without end, and they're smooth curves, no gaps, no breaks in between. So just like exponential functions, their domain is always negative to positive infinity. So for sine and cosine functions, you don't even have to think about it. The domain is always positive to negative infinity. Now, another feature of sine and cosine functions is that they oscillate, and that's the technical term for it, oscillation, meaning go back and forth. So they oscillate vertically, and the highest point they go is y equals 1, and the lowest point they go is y equals negative 1. So they're constantly oscillating between positive and negative 1. Now, this is the parent function, okay? Yes, we can play around with that, but the parent function oscillates from negative to positive 1. So the range of the sine function is negative to positive 1. Okay? Okay. Now, let's talk a little bit about period. Before we do that, let's generate a sine graph. So here we go on the unit circle. Okay, it's all about the unit circle, as you'll see. When the angle is 0, we're here, and the coordinates there are 1, 0, right? What's the sine value at 0? 0, that's the y coordinate. So when the angle is 0, sine is 0. And you see on the graph here, when the angle is 0, the y value is 0. Okay? Now, what about when the angle is pi over 2? What's the sine value? It's 1. So at pi over 2, here, the y value is 1. Sine of x is 1. At pi, we're at negative 1, 0. What's the sine value? 0. So when theta is pi, look at that. The sine is 0. Okay? So the x-axis represents the angle. The y-axis represents the value of the sine. And when we're at 3 pi over 2, what's the sine value? Negative 1, right there. And when we're back to 2 pi, the sine value goes back to 0. Yes? Now, if I were to continue, so I came here to 2 pi, and if I were to continue 2.5 pi, I would go back to sine value of 1. 3 pi, sine is 0, and then it's negative 1, and then it's 0, and then it's 1, and then it's 0, and then it's negative 1, and then it's 0. So it repeats. Okay? Now, how much of an angle did we have to go through in order to complete an initial cycle? Or in radian? 2 pi. So the angle through which you have to progress in order to complete one cycle, that is called the period of the function. So here we notice from the sine, for the sine function, the period is 2 pi. All right? We complete one cycle over a length of 2 pi. That's another way of saying it. Now, let's talk about cosine then. Same unit circle. When my angle is 0, how much is the cosine? Now it's the x-axis, right? So it's 1. So when my angle is 0, cosine is 1, right here. Okay? When I'm at pi over 2, how much is the cosine? 0. 0. When I'm at pi, how much is the cosine? That's the x-axis, negative 1. When I'm at 3 pi over 2, that's the x-axis. Cosine is 0. And then when I'm at 2 pi, that's the x-axis, cosine is 1. So do you see how the unit circle correlates exactly with an xy axis representation of the sine, right? Now, how much of an angle did we have to go through in order to complete one cycle of the cosine? Also 2 pi. So the period of the cosine is also 2 pi. What is the difference? The only difference is, so in both cases, they're oscillating between 0, 1, -1, 0, 1, -1. The difference is, just like you see on the unit circle, at at theta equals 0, sine is 0, but cosine is 1. So whereas sine starts at y equals 0, cosine starts at y equals 1. In the same exact way, domain is all reals, ranges from -1 to 1. I know that notation is new for you guys. Just know verbally that domain is all reals, and the range is -1 to 1. Okay? Yeah, eventually. So that we learn in chapter 1, but we skipped chapter 1, but we'll go back to it. So now, what else are we going to talk about here? Okay, so what if, right, you see the sine graph here? What if this was a movable graph? And what if I were to somehow hold on to the sine graph and pull it to the left a little bit? What would it look like? Well, no, that the whole thing moves. I'm not stretching it, I'm physically moving it. It would look like a cosine, like this would go here, right? This point would go here, and it would be as if I had graphed a cosine. So imagine if I just pushed it along, not compressed it, but pushed it along, right? And that came here, it would look like a cosine. So the cosine here is just a horizontal translation of a sine graph. Okay? And we also talked about the fact that if I kept circling the unit circle, I would get the same values over and over and over again. So every time I hit, I'm over 2 pi, I'm hitting the same point. Functions like that repeat are called periodic functions. Those are functions that repeat over a given interval. And so you see how the sine and cosine are related. So basically I could horizontally shift the sine and get a cosine. So the cosine is like based on the graph of a sine. Graphs like that are based on a sine graph are called a sinusoid. Okay? All right, so what do these sine and cosine equations look like? The general form is this. So we have y equals a sine bx plus c plus d. The variables are x and y. The rest, a, b, c, d, all constants, and they all have a purpose for being there. And we're going to talk about them one by one throughout this lesson and see what each one does. So first is the a. The factor a provides a vertical dilation. All right, a vertical dilation. So if I were to stretch and compress vertically. Now, if the absolute value of a is greater than 1, 3, -4, and so on. If the absolute value of a is greater than 1, then that's an expansion. Okay? If the absolute value of a is less than 1, so for example, if a is 1/3, then it's a compression. Okay? Another word for what a does is it corrects the amplitude, right? And amplitude is the height of the wave. How do we measure amplitude? We slice the wave horizontally through the middle, right down the middle. And the distance from the middle to a peak is the amplitude. It's the same distance from the center to the valley. That's A. So how much is it from peak to valley? 2a. And it's the absolute value of a. All right? Okay, so let's graph our very first sine function. Yes? Correct. Okay, so it says describe how the graphs of the following functions are related. So what's going on with g here? What types of changes is g undergoing here? Has a vertical, not a translation. Right, it's an expansion or a dilation, yes.
G has an amplitude of 3.
Exactly, it's got an amplitude of 3, so that's a vertical dilation. And here when I ask for amplitude, it's for g of x, it's for the transformed function. How much is the amplitude? Well, Dylan said it was equal to 3, okay? When I give you, on the tester quiz, I'm going to give you a grid that looks like this. It's pretty much blank. And so here, let's put the x and y axis. On the tester quiz, I want them to be, and on the homework, precisely straight, drawn with a ruler. You can draw a perfectly straight line, quote unquote, without a ruler. My eyes will see it, trust me, okay? I've been doing this a long time. Okay, now, how much is the period for the sine function? 2 pi. So it starts at x, theta equals 0, goes to theta equals 2 pi. So this is x, and this is y. So we start at 0, and now we're going to go 1, 2, 3, 4 to 2 pi. You must show me this. And then you have to label, calibrate the internal points there. So the midpoint between 0 and 2 pi is a single pi. The first point there is pi over 2 and 3 pi over 2. Question?
Is there a reason the y-axis is 1 over?
No, no reason. I just like to do it that way. You can do it the other way. You'll see later that, we're going to have to like modify a little bit. Okay, so y-axis, here is 1, here is 2, here is 3. -1, -3. Must have all of that there. Must. Now, let's graph sine of x. Sine of x, here's how you do it. It starts at when theta is 0, y is 0. And then from there, it's almost like minimal thinking. I go to maximum, 0, minimum, 0, every single time. And then I graph like that. This is f of x. And I'm going to label f of x like that. I'm drawing both. So, and the reason why I'm drawing both is if on the test or quiz I ask you to draw both, I want you to know exactly how to show it to me. By the way, these will all be drawn without a calculator. So don't, on the homework, practice without a calculator. That's f of x. Now g of x is the same, but it has an amplitude of 3. We start at the same point, and again, it goes from 0 to maximum 0, minimum 0. Maximum at 3, 0, minimum 0. Sounds good? And I label that g of x. You can or you don't have to use different colors. Whether or not you use different colors, you still have to label f of x and g of x like that. Yes.
Are we allowed to skip lines?
Like go over
So like
8.
Pi over 2, and then you skip 1, and then do pi?
Right, as long as you skipped a box there as well.
Yeah.
Yeah, you could go over 2. That's fine. All right, so that's that. Now, what if there is a reflection around the x-axis? So take a look at here. We have cosine of x and -2 cosine of x. So what are some changes that g of x has undergone? Right, -2. What does the negative do? Okay, so, huh?
It just makes it start.
It flips it vertically.
I'm looking for a mathematical term. There is a reflection around the x-axis, okay? So reflection around x-axis, and there is a vertical dilation. What is the amplitude of g of x? Nope. Positive 2. Just 2. It's a distance. So it's an absolute value. It's a distance. Okay. X-axis, y-axis. That is the straightest y-axis I have ever drawn on the Surface Pro. Look at that. The other two are pretty good too, huh? Okay. All right. So there's ever a contest. So cosine goes from 0 to 2 pi. 0, 1, 2, 3, 4. That's 2 pi. And again, we're at pi, pi over 2, and 3 pi over 2. And this is 1 and negative 1. And then eventually we're going to need our 2's. So cosine f of x, when the angle is 0, what's the cosine? 1. So cosine, it starts there. And then again, you always go like maximum 0, minimum 0, max, okay? So 0, minimum, 0, maximum. You're oscillating between positive and negative 1. Okay, this is not an absolute value graph. Does not look like a V. Remember, this is a part of a wave, so make it look like it's a part of a wave. Okay, so you need to have the valley here, the crest, the trough. It needs to be curved, and here it needs to be curved. It can't just be two lines extending, diagonally downward. Remember, there is life after this, and it extends as a wave on both sides. Yes.
Why are we starting at 1?
This is f of x. This is f of x. It's cosine. Now, g of x has a negative 2. So where is it going to start? At negative 2. And then 0, maximum, 0, minimum. Okay? All right. Sounds good? All right. That's fine, but not all waves have the same, not all sine and cosine waves have a period of 2 pi. In fact, the difference between a gamma ray and a radio wave, the only difference is that for the gamma ray, the periods are much, much, much shorter. All right? And just with that, a gamma ray can kill you, but a radio wave is totally fine. Okay? So how do we figure out how much the period of a function is? Well, it's 2 pi over the absolute value of b. That's how we get the period, 2 pi over the absolute value of b. So for example, if I have sine of 1 over 3x as my f of x, how much would the period be? 2 pi over 1/3, 2 pi over 1/3, because b is 1/3, which is 6 pi. Okay? So 1/3 is your b. So period is 6 pi, meaning whereas a normal sine function would complete a cycle over 2 pi, for this one, you have to go a length of 6 pi to complete one cycle. So it's much, much, much slower. All right? Slower means less energy for the wave. It means less harmful for you. Okay? That's a little bit of physics for you. When the period is modified, right, how are we going to graph it? What we're going to do, we're going to take the term bx plus c, and we're going to solve an inequality. This inequality. So basically, we take the term bx plus c and we're going to bound it between 0 and 2 pi. If it looks like gibberish, it'll be very simple in a minute. Okay. So here we go. How would you say f of x and g of x are different from one another? What has changed? the period has changed, right? So there is a modified period.
So does that mean when you're drawing it, one of them is still going to pi?
Correct. So yes.
Like even more.
Yeah, you'll see. So the amplitude, how much is the amplitude for g of x? 1, right? What's the period for g of x? Try again. 4 pi. Okay? Now, what we're going to do is this. We're going to take the term bx plus c. So let me do my x-axis here. Okay? So we're going to take the term bx plus c. That's this one right now. There is no c. And I'm going to put it in between 0 and 2 pi. Why 0 and 2 pi? Because that's the normal period for the cosine. Now I solve for x just like I did in algebra. So I multiply everything by 2 and I get 0, x, 4 pi. So that means, okay, on my x-axis, it's going to go from 0 to 4 pi. So 0, 1, 2, 3, 4, 4 pi. Okay? Now I know where the y-axis goes. Here. Yeah. No. It's always 5 critical points for a sine and cosine function. Always 5 critical points. Okay? Now, let me show you something here. Once you've solved this inequality and you got this, how much is the length from the initial to the final point? 4 pi. How much did you get for your period? Those need to be consistent. Okay? Now,
Can you do that with sine too?
yeah. So now, this is 2 pi in the middle, and 1 pi, and 3 pi. Okay? Okay, now look at what I'm going to do. I'm going to graph f of x, which is a cosine. Just a cosine, which goes from 0 to 2 pi. Okay? So I'm going to have to, break these down a little bit. So cosine, it'll start at 1 and go in the middle here. So take a look at the cosine. Okay? Calibrations? Yeah. As long as the x-axis is consistent. Now, let's do g of x. So g of x is going to start at the same point, but now it's going to go to pi, 2 pi, 3 pi, 4 pi, and there we go. That's g of x, and that's f of x. So do you see how the only difference is it's the same exact curve. The only difference is one completes the cycle in half the time. Okay? All right. So we know now exactly what period is. Let's talk about what frequency is. Frequency and period are very much related. Period is how long it takes to complete one cycle. So we look at one cycle. To talk about frequency, we block off a chunk of the x-axis here, and then we ask ourselves how many cycles of the wave fit in this chunk of space. So how many cycles of g of x will fit in here? 1. How many cycles?
So that's 2.
Same thing.
No.
Right. So how many cycles fit in here? 1. How many cycles of the purple? 2. So the frequency is twice as the other one. Okay? So the faster the wave, right? The higher the frequency, the slower the wave, the lower the frequency. And it's totally the same. Like if you're talking about if any of you guys are musically inclined, right? Each note has its own frequency. An F and a G have their frequency, an F and an F sharp The only difference is, that the F sharp has a little bit higher frequency. Okay? Yeah.
Isn't it the higher the frequency, the slower the wavelength?
No. The higher the frequency. Oh, the smaller the wavelength. Yes, the smaller the wavelength. Yes, and the smaller the period. Wavelength and period are the same. They're related. All right. So frequency is the reciprocal of period, meaning it's 1 over period, or absolute value of b over 2 pi. Okay? All right. So now, a bass tuba can hit a note with a frequency of 50 cycles per second. So frequency is measured in hertz after the scientist Hertz, physicist. And so this has a frequency of 50 cycles per second and an amplitude, that's A, of 0.75. And it says to write an equation for a cosine function that can be used to model the initial behavior with this note. Well, what is the general form for a cosine function? They always look the same, and it's this. Okay? Now, I'm given A explicitly, and from F, which constant can I extract from F? B. Now, frequency is B over 2 pi, and that's 50, right? So how much is B? It's 100 pi, and we can leave it as 100 pi. Huh? Yeah. Well, so now Y is A is 0.75, cosine B X. I'm not given any information that leads me to believe that there is a there is any other shift. So this is it. Okay. All right. Questions? Okay. We call these, these are basically like just plugging in problems. That one. All right. Phase shift. In the trig world, we don't say horizontal translation, we say phase shift. But for all intents and purposes, phase shift is just horizontal translation. Okay? Now, to solve for the phase shift, to get the phase shift, what you do is you take that term bx plus c. It's a magical term, that one. That's like the meat of the function, all right? And you set it equal to 0. So that's pretty much how you do it. When you solve that to 0, when you say set it to 0 and solve it for x, what do you get? Do you get negative c over b? Right. So that's what this says here. And it's always like absolute value of b. Okay? All right. So that's the phase shift. So let's do a little bit of phase shift business. Okay? Finally now, this is a function that has, this is a good function. Okay? Yeah. So what's the amplitude of this function? 2. What's the period of this function? 2 pi over 5, right. Right. I'm a little slower today. And the frequency, sorry, the frequency, reciprocal, 5 over 2 pi. For the phase shift, we're going to take the stuff in the parentheses, the bx plus c, and set it equal to 0 and solve for x. So 5x is negative pi over 4. X is negative pi over 20. So x is negative pi over 20. All right, and it's good form to say x equals negative pi over 20. What does that mean? Which direction has the function moved? Right or left?
Left.
Left. There is a plus here. Look, Jesse, there is a plus here, so it moves left. So it's consistent with this. It's the opposite of the plus there. By how much does it move to the left? By pi over 20. And we're going to have to get used to these funny fractions. It's not always going to be pi over 3, pi over 6, pi over 4. We're going to have the pi over 20. But that's fine because we're never actually going to be evaluating anything because it's an oscillation. Okay, so let's draw the x-axis here. And now what we're going to do is take the 5x plus 5 pi over 4, and we're going to bound it between 0 and 2 pi. Yeah.
Even if you don't put the new period, you still put 0 and 2 pi.
Yes. Yes. And I'll show you where the two are going to correlate now. Okay, so we're going to subtract pi over 4. So we're going to get negative pi over 4, 5x, and then 2 pi minus pi over 4. That's 1 3/4 pi, which is 7 pi over 4. Now when we divide by 5, it's negative pi over 20, x, 7 pi over 20. So do you see the negative pi over 20? It doesn't start from 0 now. It starts from negative pi over 20. And the phase shift said that that's where it had moved. The initial point had moved there. So now, here's what we do.
I thought the period has to be the same.
Okay, hang on. I'm getting there. So look, here's what we're going to do. We're going to put the first one, go 4, and put the other one, 7 pi over 20. Now, how much is the distance from negative pi over 20 to 7 pi over 20? 8 pi over 20, which is 2 pi over 5, which is what the period is. Okay? So basically, okay, yeah. So now, okay, now what we're going to do, here's where, there is a little bit of, tedious math, but we can go through this, okay? We need to find the midpoint. To find midpoint, add and divide by 2. So we're going to add the end points and divide by 2. So it's going to be half of negative pi over 20 plus 7 pi over 20, right? So that's 6 pi over 20, and that's 3 pi over 20. So the middle is 3 pi over 20. Okay, I'll try to color code. Here, the first quarter of the point there is half of negative pi over 20, 3 pi over 20. That's 2 pi over 20, and half of it is just pi over 20. And then the last point, the 3/4 of the way, it's half of 3 pi over 20, 7 pi over 20. So that's 10 pi over 20, 5 pi over 20, which is huh?
Pi over 4.
Pi over 4. Okay. Yeah, okay. Okay. So, are we okay with this? So now, we're graphing a sine, okay? And it goes, and it's got an amplitude of 2. So, sine starts at the x-axis here, and then from there we oscillate. 0, maximum, 0, minimum, 0. So look, watch how I do this. 0.
What's the red one?
Pi over 4. 0, maximum, 0, minimum, 0. It will never look any different. And now I just,